Hello, hello. So, are you able to hear me? Hello. Hello, hello. So, hello. Are you able to hear me? So, ask your friends to join Nana. Says that I will start the live session. Please come to the live chat. So, today I will be going to discuss uh, Unit 1 complete revision as well as how the questions will be appearing, how the model questions will be appearing for uh, a mid exam or sem exam. Okay. I will be discussing and what how we should write if any question comes from Unit 1 or Unit 2 or Unit 3. I will be explaining all those things today. So I want you to utilize the session such that it will help you when you are studying for the mid exam. So this session is completely very easy for the people who have missed my sessions during the early days of your semester. So especially for them, I'll be teaching all those things. So I want you people to utilize the session such that you will not be confused when any question comes from the unit one. So that is what the main agenda for this live session. So I'll be starting the live session within 2 minutes. I will be waiting for some people to join. So respected CRs, if you are there in the live session, so ask your friends to come to the live session such that uh, it will be good for me. Uh, So come to the live chat, Nana. So shall I start the session? Nana, ask someone those who have missed the class from day one and those who are not good in unit one, ask them to join rather than those who know. I can sense, I think some people are there in the live comment session. I can see them, they already know what is there, etc. etc. So I want others to come such that utilize this session, this 1 hour. Okay. So I'll be starting the session, Nana. So the first topic is nothing but introduction to quantum computing techniques. This is the topic of unit one, and in that the first topic is classical computer versus quantum computer. So before going on to quantum computer, let us be very simple. What is classical computer? So classical computers are made from transistors, microsensors, etc., etc., and they will be operating using bits. So the bits are represented using zeros and ones. If you see here, that is what I mentioned. But whereas quantum computer, it is represented as qubits. So the main difference is nothing but here it is bits, and here in the quantum computer it will be qubits, or we can say them as quantum bits also. They are represented using ket 1. So this is the symbol of ket. So try to remember these symbols, try to practice. So who are there in the class session, try to practice this symbol. The symbol is nothing but ket, which I am calling it as Dirac notation. So it is represented as, here we'll be representing zeros and ones, right? So but whereas in quantum computer it will be completely different, Nana. It is ket 0 and ket 1. So this is nothing but anything that I write in middle of this particular symbol. Let us say if I write a, then it will be ket a. Then if I write, let us say in this particular symbol, if I write x, then it is ket x. Okay, that is how the pronunciation should be look. Okay, so this is what about the first difference in classical versus quantum computer. And moving on to the second difference, here in classical computer, if the switch is on, the computer will be working. If the switch is off, the computer will be off. So, which means there will be only one state at a time. So it will be not like 0 1 or 1 0 at the same time. It will be either 0 or 1 at the same time. That is what the major difference from quantum computer and classical computer. But whereas here in quantum computer, we'll be having two or more states at the same time, that I am calling it as superposition. You need to remember this word for a while. So why? Because in quantum computer, everywhere, every time you'll be listening a word called superposition. So that is what superposition means. Which means I will be giving one example here. Let us say I'm having a fair coin which is having head and tails. Just imagine this scenario. I'm having head and tails in a coin, and I will be tossing that coin. When the coin is flipping in the air, we'll be having two states at the same time. The two states at the same time, I'm calling it as superposition. That's it, simple. So another example that I already mentioned in the class, now also I'm mentioning again. So which is nothing but a fair coin is tossed, or a fair dice is rolled. So for a dice, we'll be having six possibilities, Nana. Why there? One, two, three, four, five, six, right? So when the dice is rolling, we'll be having six possibilities at the same time. It may be one at the end. It may be one or two or three or four or five. But the thing is, when the dice is rolling, the same dice which is having six possibilities at the same time, that I am calling it as superposition. Many possibilities at the same time, I call it as superposition. That is what the major advantage of quantum computer. But whereas in classical computer, we'll be having only one possibility, either 0 or 1. That's it. Not 0 1 1 0 at the same time. That is what the second major difference between classical versus quantum. And moving on to the third difference, in classical computer we'll be having definite state, that I already mentioned in the second point itself, which means we'll be having either 0 or 1. That's it, nothing. Fan, if you on the fan, that is nothing but 1. If you switch off the fan, that is nothing but 0. We'll be having only one definite state at the same time, either 0 or 1. That is what the major difference. And moving on to here, we'll be having probabilistic state. That is what I will be explaining this, what is this probabilistic state, in the future slides. Okay, don't worry about this particular word, probabilistic. which means in quantum computer what happens is nothing but, let us say, if I toss a coin, just if I toss a coin 1,000 times, so what does quantum computer give? What is the result of the quantum computer, sir? Me, the question you will be giving me, right? The answer will be like, for example, if 1,000 times is I have tossed a coin, and I am getting 700 times heads and 300 times tails, which means I will be, as a quantum computer, I will be only giving the probability. I'm saying you, okay, if you toss a coin, the probability of getting the heads 0.7, and the probability of tails 0.3. If I add up those, I will should get 1. Then only that operation that done by quantum computer is valid. If not, if it is not getting 1, then it is not valid. That I've been mentioned already in the class. And whereas in quantum computer, everything will be represented by voltage. Okay, you need to remember this particular difference also. But here it is represented by photon, electron, and atom. That is nothing but types of qubits. So photon, electron, atom. So electron will be having two spins. I already mentioned up and down. Whereas atom consists of nucleus, protons, neutrons, and it consists of electrons. Electrons will be negatively charged particles, and atoms in nucleus will be having protons and neutrons, whereas protons has nothing but positively charged particles, whereas neutrons are having no charge, that I have already mentioned in the class. So you should remember these things. Now, whereas copying is possible in quantum, in classical, Nana. Why? Because let us say if some file is there in my desktop, I need to copy it to some other folder. Is it that is possible? Why? Because in classical computer there is nothing, there is no restriction to copy one file and move it to another location. There is no restriction. You can copy from anywhere. You can paste it anywhere. That is what the advantage of classical. But whereas here, copying is impossible. Why? Because I already mentioned in the class, if you copy anything in quantum, it will be collapsed. That is what the word I've been mentioning in the class for a while. So you try to remember that. Okay, here the output is deterministic. Deterministic in the sense the future is fixed. For example, let us say, uh, let us assume a scenario, which means like, we are playing we are playing cricket in the ground. Just assume the scenario. So when I am hitting the ball may be landing on the fielder hand, or the ball may be landing in the crowd, or the ball may be landing over the stadium. It may be anything, but the thing is, the output is fixed, which means it may be landing in the ground, or it may be landing in the hands of fielder, or it may be landing in the hands of a crowd which is there in the stands, or who are there in the stand, or it may be landed out of the stadium, which means the output is fixed. Anything, it may be anything, like the output is fixed in classical. But whereas in quantum, the output will be completely probabilistic. There will be no fixed output. We'll be only giving the probability. For example, if I hit a ball, the quantum computer says the probability of going out of the stadium is 6%, 0.6, and falling inside the stadium is 0.4. That is how the probability will be given by a quantum computer. It will not say the ball will be going out of the stadium, or the ball will be landing inside the stadium with fixed probability. So it will be giving only the possibility. That's it. That is what the major drawback of a quantum computer. It will not give the exact output. It will be giving only the probabilities. And moving on to the next example, which is nothing but, we'll be having logic gates in the classical computer. That logical gates I already mentioned, and or not, XOR, XNOT. So which are nothing but, these are nothing but the classical gates. When you are writing the question classical versus quantum, you try to define what is AND gate, what is OR gate, what is NOT gate, what is XOR. The known gates that you know. Okay, rather than just don't add everything. The 3 to 4 gates you try to have with the numbers, like, for example, 0. If 0 is my input, a NOT gate gives you 1. If 1 is my input, NOT gate gives you 0. This is how you try to include these truth tables when you are writing the differences between classical and quantum. And moving on to quantum gates, I already discussed poly X gate, poly Y gate, poly Z gate, Hadamard gate, CNOT gate, phase gate also have been discussed in the class notes. In the second unit, I will be going to discuss all those gates, what is the representations of the gates. Okay. So you try to write all those gates here itself. So you, in the seventh point, you try to write gates. So gates is not part of our syllabus, but why I teach is nothing but to get the mathematical calculations. You need to learn gates. Without teaching gates, it is nothing. So that's the reason I have been included the gates topics in the second unit. So when you are writing the differences between classical versus quantum, you try to integrate quantum gates here. In the class, in this particular point, you try to integrate the truth tables of logical gates also, such that you'll be getting the enough space or enough matter when the question comes for classical versus quantum. It will be a paka question, and it will be like, it will be giving I will be giving for 10 months. So please make sure you write perfectly. So you don't just write what is what I mentioned in this particular slide. You try to integrate this truth tables for logical gates, and all the gates that I have discussed in the second unit. You try to integrate poly x gate, poly y gate, everything, matrix representations, how the calculations has been done, etc., etc. Now if you see here, this is the major advantage of a quantum computer. If you see here, in classical computer, it can be hacked. No, anyone can hack some classical computers or classical internet or something. But whereas in quantum computer, it cannot be hacked. Why it cannot be hacked? That is what the main question you should ask yourself. So sir is saying it cannot be hacked, then I butify this point, and then I will be remembering in the exam, and I will be writing. That is not I want. I want you to answer yourself why it is not hacked. Why? Because when a quantum system which is in superposition, just assume a coin is flipping in the air. If I try to know what is there in the coin, let us say I know as a uh, engager, I know there is only two possibilities, head and tails. But someone comes randomly and it does not know whether the coin carrying head and tails or some other information, etc., etc., right? So that time what happens is nothing but uh, when it tries to know the information what is there in the coin, it will stop it. What happens if we stop that particular coin which is flipping in the air? The wave will be collapsed, which means he cannot see anything. In the quantum computer, when the quantum computer is having in superposition, when someone tries to see the information what is transmitting from one computer to another computer, or one person to another person, it will be collapsed. Which means that is the main reason I am mentioning that it cannot be hacked. So I can mention here 100, it is 100% hack proof. It is 100% hack proof. So you remember it. Okay. Now moving on to the ninth point. Already I mentioned data is stored as zeros and ones. Here, data is stored as wave amplitudes. That wave amplitudes, you need to remember this word. Okay. Now moving on to the 10th point, communication uses electrical signals, which means our classical internet will be using electrical signals to transmit our information one to other, which can be hackable. Again, I've been mentioning that, which can be hackable. But whereas in the quantum computer, it uses entangled photons, which cannot be hacked, which is 100% hack proof. Again, I've been mentioning here, which is 100% hack proof. Okay, you try to remember this. Now, what is a qubit? Before going on to the next topic, I wanted to discuss what is qubit. So, qubit is also known as quantum bit, that I already mentioned here. If you see here, it is qubit is known as a quantum bit. It is represented as ket 1, ket 0. That you try to write the definition from the above slide. Okay, you try to write the definition. Now, that is which how it is represented. It is represented as ket psi. What is this? Ket psi, which means if you see, if I'm writing the spelling, ket psi, this is nothing but in the ket will be, it will be called psi. Ket psi is equal to alpha ket 0 plus beta ket 1, whereas alpha and beta are nothing but probability amplitudes. Here in this particular exam, this is how the quantum state is represented. But whereas in classical, either 0 or 1, that's it. But in quantum, we'll be having this particular state. Ket psi is equal to alpha ket 0 plus beta ket 1. To prove it is valid, then this is the equation. Mod alpha square plus mod beta square should be equal to 1. So the probability of measuring ket 0 is, and the probability of measuring ket 1 is, what is the probability of measuring ket 0? Kindly please answer me in the comment section. Those who are there in the class, Nana, try to answer me. What is the probability of measuring ket zero? Kindly answer me. It should be interactive, Nana. That is what the main reason. Why? Because you are giving out of time for me, and I'm also spending the out of time rather after the college. So it should be energetic and it should be like interactive. So I'm asking, what is the probability of measuring ket zero, and what is the probability of measuring ket one? That is what my question is. Can anyone please come to comment section, Nana? It is not about what is the probability of measuring ket zero. That is what my simple question is. You are having answer there itself. No, 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 no. I am not asking the value. I am just asking uh, the formula. I think the answer is correct, but I want the formula. That's it, Kavya. Good. You are given the perfect answer, Magar. I want the formula rather than the value. You type in English itself. So why? Because typing mathematical equations in the comment section is not possible. Just you type answer in English itself. I will be reading out. Mod alpha square. Super, super, Upendra. That is what I want. So probability of measuring Ketzer is mod alpha square. Navya, you are giving the answer, but I want the formula. So before K zero, if I give any question like give asking you probability of measuring zero, that means before zero what is there? You need to check this. Before zero, we are having alpha, which means mod alpha square, which is the probability of measuring zero. And if I ask what is the probability of measuring one, then you need to see before what is there before one. That is nothing but mod beta square. Mod beta square. That is what before one is. Okay, which means if I add the summation, if I add the sum, then that should be equal to this particular equation. That should be equal to one. That is what I want. Super, super. Sai Varan, the answer is correct. Mod alpha square plus mod beta square, which means the probability of measuring one will be mod beta square. That is what Hussein, super. And the probability of measuring zero is mod alpha square. That is what you need to remember. And whereas this alpha and beta are nothing but probability amplitude. This is what about the representation of qubit. So you try to remember these equations. And now I'm moving on to the most important topic, which is nothing but fundamentals of quantum. So the question may be like fundamentals of quantum, principles of quantum, foundations of quantum. There's some different terms I will be using when I'm giving the question in the examination point of view. The answer is same. It may be any type, principles of quantum or fundamentals of quantum or foundations of quantum, anything, but the answer is same. The answer is nothing but the first foundation or fundamental is nothing but superposition. I already mentioned two or more states at the same time. So try to keep a sentence here at the same time. At the same time, it is much most required. Why? Because at the same time, try to integrate. I'm not able to write here at the same time. Okay, at the same time. Try to integrate this particular sentence in the when you're writing. So if a particle is having two or more states at the same time, then I'm calling it as superposition. That's it. Can you give me the best examples for superposition in the chat box? Nana, ask others also. Why? Because I'm going very slow. Why? Because it is once this unit is clear, then you can easily understand unit 2 as well as unit 3. So what is there in unit 2 is not there will be there in unit 1. So why I'm going slow is nothing but I wanted to give that pinpoint explanation from start itself. Why? Because some most of the people have missed my early sessions. That is the main reason I'm going very slow. But when it comes to unit 2, I will be going very fast. Why? Because if you learn unit 1, then you will be understanding unit 2 very easily. Tossing a coin, super Sushmita. Tossing a coin. Why? When it is flipping in the air, we'll be having two states at the same time, head and tails. So until I stop the coin, it may be head or tails, which means the same coin having two or more states at the same time. That I am calling it as superposition. Another example. Still, some other examples. Super example, Anna. Rolling dice, super Chandra. And what is the cause of that rolling dice? You try to explain this explanation also when you are writing in the examination. When I'm rolling a dice, we'll be having six possibilities at the same time. Either it may be one or two or three or four, it may be five or six. Until it stops, it will be having six possibilities for the same dice. Only single dice will be having six possibilities. That is the reason we are calling the rolling dice example as superposition. This is how you need to mention when you are writing in the examination. Clear? Rainbows, super rainbows. Okay, nice. Double slit experiment, super Shivakumar. So why double slit experiment, Nana? Why? Because we'll be passing the light through two slits. So until we see, it will be in interference pattern. But when I observe with a particular pattern, it will not. I will be only seeing the lights hitting the screen. That's it. Okay, that is super example. Super wonderful. I want this type of things that should be there in the comment section. And the main definition, you once you see here, superposition means a quantum system or a quantum system or quantum particle can be in multiple states at the same time until it is measured, which means until I stop the coin, it should be flipping. Then that coin is nothing but it is in a superposition. That's it. Simple. Now, a quantum system can be off, on at the same time. That is what I mentioned. Coin flipping, dice, pass or fail in the examination. Why? Because I was expecting this particular example when you are answering in the comment section. Why? Because I've been mentioned this example. What example I mentioned? Until let us say the results has been announced, and you are opening the digital campus. The same student maybe pass or fail until he is logged into his particular credentials. He may be pass or fail. Either one outcome will be there until he log in. So until he log in, he will be in two states at the same time, where that is nothing but pass and fail. That is what I have been mentioned here. Digital campus exam. So try to uh, integrate these examples when you are writing in the exam. So the same equation comes. So anytime when I ask you, you try to answer these particular equations, Nana. So I want you to answer whether this particular qubit is valid or not. Alpha is equal to 0.4 and beta is equal to 0.6. Nice, nice. Kavya, Kavya, haven't seen. No issues. So I want you to answer me whether given alpha is equal to 0.4 and beta is equal to 0.6, check whether it is valid or not. How, Amma? Sushmita, how? You once calculate. I want the calculation. Valid. Okay, fine. What is the value of mod alpha square here? Value of mod alpha square, and what is the value of mod beta square? And try to add up them in the comment section itself. Not valid. Why? Why? I want that mathematical calculation to be done in the comment section, Anna, rather than just saying valid, not valid. Please make it fast. Simple calculation. You know the formula. Mod 0 point whole square 0 point. I think it is valid, right, Shiva? Then it should be valid. If it is equal to 1, then it should be valid, right? Shiva? Mahadev, super. What is the value of 0 0.4 whole square? And what is the value of 0 0.6 whole square? 0 point, I think 0 0.4, it will be 0 0.24, and 0 0.6, it will be 0 0.36, which means I'll be ended up getting 0 0.52. If 0 point, I think 0 0.52 is equal to 1. Is it equal to 1? Navya, you are saying it is valid, but the thing is 0 0.4 whole square plus 0 0.6 whole square is nothing but 0 0.52. I need to get 1 right. So there is the equation itself states that we require 1. Right, mod alpha square plus mod beta square should be always equal to 1, then only the qubit is valid, right? Not valid. So that is what in this particular example it is not valid. So if you see here, it is not valid. Now try to check this example, Anna. Mod alpha. Why? Because why it is not valid? If you see here, mod, you should not give whole square here, you should give mod. You try to remember this. Always use mod. Okay, mod 0 point whole square plus mod 0 0.6 whole square, that is nothing but 0 0.216 plus 0 0.236, which I'll be end up getting 0 0.52, which is not equal to 1. That is why I'm saying this qubit is not valid. Now try to check this condition. 0 0.6 plus 0 0.8. Nice, Nana Sushmita. It is, that is what I want. That is for the right answer. Now try to check valid. Super, right? What is the value of alpha square? Mod alpha square. And what is the value of mod beta square? No. I think once check. Arif, once check. Mod alpha is equal to 0 0.6 and beta is equal to 0 0.8. Try to check it in the formula, Arif. A small calculation, you are taking much time. 0 0.36 plus 0 0.64 is equal to 1. So it is valid, right? So that is what Kavya, Sushmita, you're doing wonderful. So that is what valid. Super. Shiva. So which is nothing but it is a valid qubit. Why? Because 0 0.6 whole square gives you the value of 0 0.36. Again, I have been mentioning you should keep mod when you are writing in the exam. I will cut the marks if you are not giving the mod. Okay. 0.08, 0 0.8 will be end up getting 0 0.64. If the value, if you add the sum, then it will end up getting 1. That is why I'm stating it as a valid qubit. That's it. Nice. Sandhyana, super. Arif, super. That is what the correction. Hussein, Re, Hussein, Navya, super, Nana. Upendra, super. That is what. Now, uh, in this particular example, I will be giving directly. Alpha is nothing but 1 by root 2 and beta is nothing but 1 by root 2. If again here the same thing, same issue, mod again here. So you try to integrate mod here. Mod alpha square plus mod beta square. This is nothing but 1 by 2. 1 by 2 will be end up getting 1. So it is valid. So please remember, this is the equation of superposition, Anna. If I check the probability of alpha, then I will be getting 0 0.5, 0 0.5. And if I check the probability of beta, again I will be getting 0 0.5 in this particular example from this equation. So that's why the equation I am calling it as equation of superposition. You try to remember this. mod size ket size is equal to 1 by root 2 ket 0 plus 1 by root 2 ket 1 is the equation of superposition. You try to remember it. Okay. Now again these particular things blah blah I will be given validate everything here. 3 by 5 is nothing but alpha and 4 by 5 is nothing but beta. So mod alpha square plus beta square, again here the same mistake again repeated. Don't repeat this in the exam. Okay, you'll be end up getting 25 by 25, which is nothing but 1. So this is nothing but the qubit is valid. Now moving on to the second most important fundamental, which is nothing but entanglement. So I have discussed the example in the class. I have taken the names of two students. I don't know whether the what are those names. Again, I'll be mentioning again and again. Let us say I'm having two students, student one and student two. They are roommates. Remember this condition. They are roommates. So since they are roommates, before a day of my exam, they started studying combinedly in the room itself. Then in the next morning, they are sitting in the different rooms. Let us say one is sitting in the 401, another is sitting in the 301. There is no connection between them, and the paper has been distributed for the students in the examination hall. And what they have studied in the night, which is a day before my exam, the questions are the questions that I got in the paper are similar, and what student one has been written and the same thing the student two is written. Why? Because they have studied overnight. Okay. And when it came to correction for me, then I thought student one and student two has been copied. Then I started investigating whether there's what is their seating arrangement. Then I came to know one is sitting in the 401, another one is sitting in the 301. There is no possibility for copying. That particular example here is nothing but entanglement. If particle 1 and particle 2 are entangling each other, if there will be no physical connection between particle 1 and particle 2, but particle 1 defines the state of particle 2 even they are far apart. That is nothing but entanglement. This is the most important fundamental. So I am talking about two fundamental particles, so two students. That is why equation will be shifted to two qubits. In the next slide I'll be seeing that equation also. If you see here again, uh, entanglement is nothing but the connection between two quantum particles, such that the state of one instantly determines the state of other. Even not given. This is wrong. Even you try to write correct it. Even even they are far apart. So two particles perfectly linked no matter how what is the distance. Okay. So this is the equation I have been mentioned earlier. This is the equation of superposition and this is the equation of Hadamard gate. Okay, for one particle. But when I am talking about two particles, if you see here, ket phi is equal to 1 by root 2 0 0 0 0 is nothing but this is student 1 and this is student 2. One is student 1, another one is student 2. Same here also. Student 1, student 1, and here this second one represents student 2. So you try to remember it. So I am talking about two students studied overnight. So if student, for example, 0, for example, if the value is 0 means the question coming from the out of syllabus or out of box that they have learnt in the night. So then if student 1 doesn't have to attempt, then student 2 will also not attempt. Why? Because they haven't studied. If student 1 attempts, then student 2 will be also attempting. Why? Because they have studied the same topics and the same syllabus overnight. That is what the fundamental of entanglement. Let us say if particle 1 is 0 and then particle 2 will be also 0. If particle 2 is 1, then the particle 1 is 1, then particle 2 will be also 1. That is the fundamental of entanglement. This equation is also known as Bell state equation. You try to write this also in the examination. Okay. That is what about entanglement. That is what I mentioned. If the first qubit is measured in state 1, what will be the state of second qubit, which means I have been mentioned here. If the first qubit is 1, the second qubit will be 1. If the first qubit is 0, the second qubit will be 0. That is what about entanglement. Now moving on to the third important fundamental, which is nothing but uncertainty principle. So simply remember, if uncertainty principle, if you forget the definition, you try to look up. Then you will be seeing it's the fan rotating on your head, on the top of your head, not on your head, on the top of your head. Okay. So let us say I'm marking the wing one as one, wing two as two, and wing three that as three. And I started switching on the fan with high speed. Then I ask you to find whether where the one is exactly rotating and what is the speed of one. Is that possible? No, right? So what does uncertainty principle states that is nothing but it is impossible to know both exact position and momentum of a particles at the same time, simultaneously here in the sense at the same time. You can't see position and speed at the same time. That is what uncertainty principle states. Okay. So fan rotating, I have been given this example. Okay, which is very important formula, Nana. You try to remember this formula. Mod mod sorry, delta x into delta p is greater than or equal to h by 4 pi. Here delta x is nothing but change in position, delta p is nothing but change in momentum, whereas h is nothing but Planck's constant. You already know what is the value of Planck's constant, and you should know what is the value of pi also. If you see here, Planck's constant, which is the value, which is nothing but 6.63 into 10 to the power minus 34 joules, is the value of Planck's constant. So I have given one example here. I have said that a particle is confined to a region of length. I've been given delta x. Delta x is nothing but 0.005, and estimate the minimum uncertainty in momentum. Then you already know what is x, and you try to convert into meters. Then I will be end up getting 5 into 10 to the power of minus 4. And if I send delta x this side, and I will be remain the momentum will be remaining this side. So delta p is equal to h by 4 pi into delta x. And you know the value of h, which is nothing but 6.626 into 10 to the power minus 34 into minus 4 into 4 4 into the pi value 3.4, and you try to substitute this equation, and then you will be end up getting 1.0545 into 10 to the power minus 31 kg meter per second. So that is how you need to calculate. You try to take any example here, x is equal to some other example also, which is very easy to calculate. Okay, and try to find p when it in the examination. Now moving on to another most important fourth fundamental of quantum, which is nothing but wave particle duality. Name itself has duality. So this states that a dual role, which means a double action, is a hero having a double action in the same movie. So that is nothing but wave particle duality. For example, let us say water can travel as waves, and the water droplets is nothing but we call them as particles. So they are having two properties. Some errors has been there in the notes. Wave like, and here also not light, and here also same thing, wave like. So quantum particles can be in both wave like and particle like behavior at the same time. Then I am calling it as wave particle duality. Every microscopic particle behave like as particle and wave. So that is what I've been mentioned here. And if you see the equation of wave particle duality, which is nothing but the de Broglie equation. So lambda is equal to h by p, whereas lambda is nothing but the wavelength, and h is nothing but again Planck's constant, p is nothing but momentum. So I have given example here. Try to substitute all those things in the exam, and you try to gain this value 3.31 into 10 to the power of minus 10. And moving on to the most important and confusing topic, which is nothing but quantization. So before moving on to quantization, I want to discuss one thing. Let us assume we are having the lift in our block, right? So that lift will be stopping at 0, 1, 2, 3, 4, right? We are having only 4 floors. From 0 to 4 it will be stopping. So just assume that I stopped the lift in between 0 and 1. Is that possible to get out of the lift? Please let me know in the comment section. We are having uh, 5 stages in our campus: 0, 1, 2, 3, 4. So if the lift is stopped at one station, we can get out. Let us say if the lift is stopped at 0, I'll be getting out on the ground floor. If the lift is stopping at fourth floor, then I'll be getting out from the on the fourth floor, right? But what if I ask you to stop in between 3 and 4? Is that possible to get out? That is what my question is. Is that possible, Nana? Is that possible to get out from the lift when it is stuck in between 0 and 1, or 1 and 2, or 2 and 3, or 3 and 4? Is that possible? Please let me know in the comment section. Impossible, right? That is what. So, but whereas classical physics states that uh, it is possible, but in real life it is not possible. That is explained by the concept called quantization. So it is not possible, it is impossible. That is what quantization has been stated by proving it experimentally. Super, super. Gora Sushmita, Shivakumar, Rehan Hussain, Shivakumar, Vipendra Kumar, Supanana, Kavya. So that is what. So quantization means certain physical quantities such as energy, angular momentum, and electric charge can only have specific fixed values. That is what you need to remember. They are only having specific fixed values. What are those specific fixed values in the lift example? 0, 1, 2, 3, 4, etc. These are the specific fixed values. Then they in the specific fixed values only the lift can stop. Then only the person who is coming on the lift can come out. So these are nothing but the specific fixed values. So they cannot take any arbitrary values. Any arbitrary values in the sense zero, in between 0 and 1, 1 and 2, 2 and 3, 3 and 4, etc. etc. That is nothing but I am calling it as arbitrary values. Nature allows certain allowed values and does not allow values in between. That is what I've been mentioning. So if you see here, an electron which is spinning around the nucleus will be having fixed sizes. N is equal to 1. I think some example is it is not missed. So energy level is equal to 1, energy level is equal to 2, and energy level is equal to 3. So it can stay either at 1 or 2 or 3, not in between the arbitrary values. Okay, that is what about quantization. So I've been mentioned here an electron inside one atom occupy energy level 1, energy level 2, energy level, but not never. So you try to see this point, but never between two energy levels. It is like in between 1 and 2, 2 and 3, or 3 and 4. This is called quantization of energy. You try to remember this. So I already mentioned lift. And also another example here is nothing but steps. Why I mentioned steps here? Why? Because let us say I am standing on the steps. So in I want you to. I am giving a task for a student. I want you to stand in between step 1 and step 2. Is that possible? Is that possible, Nana? If I ask you to stand in between step 1 and step 2, is that possible? That is what I am asking. Is that possible, Nana? Yes or no? Please come to comment section. Is it possible to stand in between 1 and 2? That is what my question is. I given a task. No, 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 right, Hussein. Super. Another one, another example I've been mentioned here is nothing but ATM notes. Why? Because let us assume ATM is having yes, yes, Nana. Super. ATM is having, let us say, hundreds, 200s, and 500 notes in the box. But what I typed is nothing but I have typed 109. Is that possible for the ATM to give withdraw my money? Is that possible? Is that possible to withdraw 109 when the ATM is having only hundreds, 200s, 300s, 200s, and 500s? Is that possible? No, right? That is what Shamraj, nice. It is not possible. That is what the quantization states. It is not possible to perform this type of things in real life. That is what the quantization says. Now I've been given one example: quantization in an atom. So consider an hydrogen atom that in the hydrogen atom the electron revolves around nucleus. According to classical physics, electron should able to stay any. It is not possible. So, but experiment shows that it will be having a fixed energy level. That energy level example have been mentioned here. So wow, the hydrogen atom energy level is nothing but En is equal to minus. You try to see this minus also. Something they have missed, I think. Minus 13.6 uh, EV by n square is the energy level of an hydrogen atom. Okay, where n is nothing but the principal quantum number, which is nothing but if it is staying at close to nucleus, then the n is equal to 1. If it is in the second shell, the n is equal to 2. If it is in the third shell, the n is equal to 3. N will be varied based on the energy level of the electron that is shifting. Okay, and En is nothing but the energy level of an electron, not an atom. Okay, so for example, if it is staying at 1, the energy level will be minus 13.6. If it is staying at 2, n is equal to 2, which means the second shell, the energy level will be 3.4. If it is staying at 3, the energy level will be minus 1.5. If it is staying at 4, the energy level is nothing but minus 0.85. So, yeah, I've been given here. If you see here, suppose my electron or my atom is staying at energy level is n is equal to 1, and its energy is nothing but n is equal to 1. It is nothing but minus 13.6. If it absorbs energy and it needs to jump, if it is absorbing this minus 13.6, it can jump to minus 30, minus second energy level. So the energy that is required for an electron to jump from energy level 1 to energy level 2, the formula is nothing but delta is equal to E2 minus E1, Nana. So if I want my energy, my electron or my any other thing wants to jump from energy level 1 to 2, then my formula is nothing but the energy level of second minus the energy level of first, which is nothing but minus will be cancelled. That is nothing but 10.2 EV. Then only the energy level, the electron which is which is there in the energy level 1 can jump from energy level 1 to 2. So the next more important topic is measurement of qubit. Nana, is that clear till this particular topic? Then I can move forward. Is that clear? I am going slow. I can understand. Should I increase the speed also? You please let me know in the comment section. Is the speed is good or should I increase the speed? And also answer me. Is that clear till now? Two questions you need to answer. Should I increase the speed? And also, is the core topics clear till this point, until quantization? Yes, but should I increase the speed? Try to do the comment increase. If it is not required, not required. Now moving on to the next. Nice, nice, Nana. Okay, Hussein. Okay, Hussein. I will be increasing some speed in the concepts. Okay. So measurement of qubit. I already mentioned when you measure anything. Well, let us say I am flipping a coin. Let us say my coin, I have tossed. Okay, Bunny Jan. No, sir. Go slow. I think I'm going slow, right? Okay, Arif. Okay, Arif. I will continue the same speed. No issues. The thing is, You people please be active in the comment section, such that it will be encouraging for me from my side also. So let us say, what happens when you measure a qubit? That is what the main question is. So let us say I have given a task, like for a quantum computer to compute a coin is tossed 1,000 times. I wanted to know the probability how many times that the coin will be heads and how many times the coin will be tails. Let us say I have given a task to the quantum computer. So what happens? So at the end of the day, you need to know the result, right? So to know the result, you require measurement. To know the result, you require measurement. So if you are not doing good measurement, the value the quantum system will be collapsed. That is what I mentioned here. I think somewhere I've been mentioned that about collapse. Okay. So what happens when I measure a qubit? Let us say, let us take the same example I've been mentioning from the class, the starting itself. When I when I am tossing a coin, and when some random guy comes, and when the random guy comes, he needs to know what is there in the coin. Then what happens? He will be stopping that coin, right? Then only he will be knowing where what is there, head or tails or some other value or some other thing is there hidden on the coin. So what happens if we stop? It will be collapsed. It will be collapsed to either it may be head or tails. One definite state, it will be collapsed. That is what happens when you measure a qubit. When you measure a qubit, it will be collapsed to one definite state. That is what I have mentioned here. If you see here, quantum measurement is the process of observing or measuring a quantum particle such as electron or photon to determine the state. Okay, what is the value at the end of the calculation? For that we require quantum measurement. Unlike classical physics, measurements in quantum mechanics does not simply reveal the state, but it change the state of a particle. That is what I am saying. So what happened when the coin is flipping? Suddenly a stop. It collapsed the superposition state, right? So which means it is collapsing. It is collapsed to either head or tails. Only one definite state. Or simply another example: if the dice is rolling, I have stopped. It will be stopped at one position. Either it may be one or two or three or four or five or six, but when it is rolling, it is having six possibilities at the same time. So measurement collapses the quantum state to only one definite state. That is what the measurement of the drawback of measurement of qubit is. Okay. So if you see here, again the same example I have given here. Ma 3 by 5 plus 4 by 5 get 1. So you will be getting the 36% as probability of 0, and 36% of the probability of 64% as the probability of 1. So hence, what a measurement gives us is nothing but when you measure. So probability 1 is having probability of 1 is having more possibility, then the qubit state will be collapsed to 1. You will be not able to see this probability of 0 or 0 qubit. So it will be collapsed to ket 1. Why? Because it is having the more probability, which is having in this particular example, probability of 1 is having the more probability, is 64%. That is the reason it will be collapsed to 1. So when you measure, you will be getting two results, but the thing is, it will be collapsed to the most important state. In this particular example, the most important state here is nothing but 1. That is why the qubit is collapsed to ket 1. I have given a big example, a qubit example here. If you see here, I think this example she's having written the perfectly. So here, probability of here, I think 0 0 get 0 0. So please make a correction. 1/4. Here I think we'll be having 0 1 2 qubit system. I have mentioned for 2 qubit system we'll be having four possibilities. Okay, 0 0 0 1 1 0 1 1. So if I ask what is the probability of 0 0, then you should answer me this answer. What is before probability of 0 0? That is what you need to see. If can anyone say what is the probability of 1 1? Probability of 1 1 in the example that you are able to see on the screen. Please let me know in the comment section. I want you to answer probability of 1 1, and let me know in the comment section, Anna, what is the answer of 1 1. You see what is there, what is the value before 1 1, and you try to apply the formula mod square. That's it. That will be your value. No, no, no. 3 by 16. That is what. What is there before 1 1? Root 3 by 4, right? You try to write the formula mod alpha square. Before what is there before 1 1? You try to just have that mod square to it, then you will be end up getting the value. And what is the value of 0 1? 0 1. 3 by 16. Nice, nice, Sushmita. Nano narrative. I think he calculated the value, no issues. Nice, Kavya. Sandhyana, good. I want the value of 0 1. 0 1. 1 by 4. 1 by 4, I think. One sec, Nana. Sushmita. 1 by 16. Super. So, what is there before 0 1? You try to apply mod square. Again, the whole square is given. So, try to correct this. Why? Because you don't practice this. Okay. Mod should be there. It is mandatory. If you see here in this example, the probability of measuring second qubit as 1. If you take the thing, this is the in this particular qubit 0 0, first 0 represents first qubit and second 0 represents second qubit. And in this particular example, first 0 represents first qubit and second 1 represents the second qubit. And in this example also, first qubit represents 1 and second qubit represents 0. In this example also, first qubit represents 1 and the second qubit represents 1. So what I have been asked here, the probability of measuring second qubit as 1. If you see in this example, second qubit 1 is having here and here. You try to add up those. Okay, I want the answer, Nana. Second qubit as 1. Please let me know the answer. Harsha, good, Nana. Second qubit as 1. You try to add up those. Mod square, you add up them. That's it. What is the value? Second qubit as 1. We are having second qubit as 1 in this part here only and here. If I ask first qubit as 0, this is the example and this will be the example. Right? You please add up, Nana, and let me know the answer. Make it fast. I already mentioned you try to have a pen and paper. No, 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 no. Try to add up second qubit as 1. 1 by 4 whole square plus root 3 by 4 whole square. What will be the answer? I am asking second qubit as 1. If you see here in the 1 2 1 2 1 2, you see, so where the second qubit 1 as there in this particular four things. 4 by 16 or 1 by 4, sir. Nice, nice. Super. That is what the answer is, Nana. If you see here, you'll be end up getting second qubit as 1 means you see only the second qubit. You don't see the first qubit. You'll be end up getting 4 by 16. Next, if you want the first qubit as 0, you check the first qubit 0 terms and you add up them. You'll be end up getting 5 by 16. And first qubit as 1, you'll be end up getting these results. So e power pi by 2 whole square is nothing but 1. You remember this. The value of e power I pi by 2 whole square is 1. Okay. So you remember that. Now, uh, quantum particles are extremely sensitive when we measure them. Measuring device interacts with the particle. This interaction changes the quantum state or collapses. That is what again the same thing I've been mentioned here. So the importance of measurement is nothing but when you are performing any operation or when you are performing any calculation, at the end you need to know the results, right? So that is what I've been mentioning. In quantum computer, at the end of the quantum computation, the qubits are measured to obtain the final answer. So rather than just performing action. I want the result, right? So that is at the end, I require result. That is why I require quantum measurement. In quantum communication also, if I am sending a message hi from my side, then the second user will also should see hi, right? So which means I require measurement from their side also. That is why in quantum communication it is required. In cryptography also we require quantum communication or quantum measurement. Okay. So now moving on to the very important topic, which is nothing but overview of quantum systems, Nana. So a quantum system, let us say, if for example, for me, if I am having the quantum properties such as superposition, entanglement, or wave particle duality, or quantization, or uncertainty principle, then I am a quantum system. If I am obeying any of those principles, I am a quantum system. So quantum system is nothing. Don't think what is a quantum system. Quantum system and into an don't think. Keep that in mind. So what a quantum system is nothing but which obeys the foundations or fundamentals or principles of quantum computing. That's it. The fundamentals are nothing but superposition, entanglement, wave particle duality, quantization, etc., etc. Right. So any physical system that obeys these quantum principles is nothing but a quantum system. Say that is what I've been mentioning. A quantum system is any physical system that follows the laws of quantum mechanics. The laws of quantum mechanics are nothing but the fundamentals of quantum instead of classical physics. Quantum systems are usually very small, such as electrons, photons, atoms, and molecules. You need to remember this. They are very small and very sensitive. That sensitive, I am calling it as fragile. In the second unit, I already mentioned what is fragile. Okay. These tiny particles behave differently from everyday objects like cars and other physical objects. Okay, they will be having superposition. They may behave in entanglement. May behave as wave particle duality, which is very weird compared to the classical cars or motors or bikes or etc. Now, what is a quantum system? A quantum system is any physical system that follows quantum mechanics. Okay, so examples include electron moving around the nucleus, photon traveling through the space inside the quantum computer. This system exhibit quantum properties such as superposition, entanglement, uncertainty principle, wave particle duality, quantization. If any quantum system that is a quantum system, then it should obey these particular principles, Nana. So you need to remember this. If I say any system is a quantum system, then they should obey these particular five principles. Now moving on to the most important overview of quantum system. In that, first one is nothing but an electron. So electron is nothing but a negatively charged particle or negatively charged subatomic particle, which is so electron is nothing but let us. I will be drawing here. Let us say I am having nucleus, and electron is nothing but here we will be having electron. It will be revolving around a nucleus. Revolving around nucleus, which is nothing but a negatively charged particles which is revolving around the nucleus. So it is represented by e power minus, which is nothing but negative. It represents negatively charged. So electrons are responsible for electricity, electronic devices, and quantum computers. So electrons can behave like particles, waves, and exist in superposition. That is why I'm calling this electron is nothing but a quantum system. Become entangled and occupy discrete energy level. Discrete energy levels in the sense in quantization will be discrete energy levels in the sense 1, 2, 3, 4, which means it is obeying that quantization fundamental also. That is why I'm calling electron is a quantum system. So the electronic charge is nothing but minus 1.602 into 10 to the power minus 619 coulombs. So this is the electronic charge of a single electron. You try to remember this. So again, when you are writing electron, you try to mention the charge also, e power minus. Okay. Let us say, suppose we are having 10 electrons flowing through a wire. What is the total charge? Total charge is nothing but 10 into the particular charge of one single electron minus 1.602 into 10 to the power minus 19. So when you are multiplying or when you are calculating the total charge, this minus will be eliminated. That is the reason I have not included minus in the example. So you'll be, the charge should be always positive. That is why I have not included minus. So the don't be panic. Sir have written minus on the above equation now plus on the below equation. Don't be panic. Why I may been eliminated minus is nothing but when I am calculating the total charge, it should be always positive. It should not be negative. That's why I have removed minus in this from this equation, and I have calculated positive here. Okay, that is what about electron. Now moving on to another physical quantum system, which is nothing, which is most important, which is nothing but photon. A photon is nothing but the packets of light energy, nana, or small packet. That small packet I am calling it as quantum or quanta. So before writing quantum here, you please write quanta, not quantum. Okay, so that small packet I'm calling it as quanta. Small packet of light energy is calling it as quanta. It has no mass, no electric charge, and it travels at the speed of light in a vacuum. That speed of light is nothing but 3 power 10, 3 into 10 to the power 8. That is the speed of light. Okay. Now, photon energy. So the single photon, the energy of the photon is calculated using E is equal to h into f. H is nothing but again Planck's constant, and f is nothing but frequency. Suppose the given frequency is 5, f is equal to 10 to the power 14, and if I ask you to calculate the energy of an photon, the formula will be E is equal to h into f. You try to multiply frequency with respect to Planck's constant, then you will be end up getting E is equal to 3.313 into 10 to the power of minus 19, which is nothing but the energy carried by one single photon. This is the energy carried by one single photon, Nana. You try to remember this. Okay. Now moving on to another most important physical quantum systems are nothing but atom. So an atom is nothing but the smallest unit of an element that retains its chemical properties. It consists of, if you see here, it consists of nucleus and electrons, which is revolving around the nucleus, and electrons is negatively charged particles, and nucleus consist of neutrons and protons, and protons will be having positive charge. Okay, and protons consist of positive charge, and neutrons will be having no charge. So that is the structure of the atom. Okay, which is simply you remember as small as atom is nothing but the smallest unit of an element. So electrons will be carrying the negative charge, and whereas neutrons will be nucleus having neutrons with consist of no charge, and protons which is consisting of positive charge. That is what about atom. This is the overview of the physical quantum systems. So inside nucleus, protons will be having positive charge. That is already I mentioned. Okay. So an hydrogen atom contains one proton, one electron, and usually no neutron. Okay. That is what about the overview of quantum systems. I think till this point everyone is clear, right? Still anyone is having any doubt in any calculations? Let me know, Nana, in the comment section. Let me know in the comment section, Nana. Before going, why we need to learn quantum. Before going on to that topic, Sai Charan, hi Sai Charan, how are you? Hmm. Nana, till this point is everyone is clear, right? So please answer me in the comment section. If everyone is clear, then I will proceed to the next topic. Time is running fast. Please don't waste my time and don't waste your time also. Uh, Everyone is clear, right? Nice, nice, nice. Nano narratives. Thank you for the confirmation. So moving on to the next topic, why we need to learn quantum, Nana. That is what the next topic is about. So before going on to that, why we should learn quantum is nothing but which will be the next technological revolution in the IT industry, which is nothing but quantum. That is the reason we need to learn quantum. Similar to how computers and internet transformed the world. So initially, the computers were being very room size. Then it is available now with a compatible size, right? So the evaluation, how the classical computers are evolved from the years, the same situation where our quantum is also standing. So our quantum now having a quantum computer with the size of a big room. So now it should evolve over the years in the future. In after 50 or 30 or 40 years, it will be compatible as a classical computer as of now. So that is why we should learn quantum. Why? Because it is there in the early stages. If we learn quantum, then we can be a scientist, then we can be a founder of a classic quantum computer, etc., etc. That is why we should learn quantum. So scientists believe quantum technology has potential to solve problems that are impossible. So try to remember, this is the main reason, that are impossible and take an extremely long time. For a classical computer, uh, which is taking a long time, we can solve it in seconds in quantum computers. So today computers are becoming increasingly powerful, but many real world problems are so complex. Okay, that is what the main reason of for classical computers, why we require quantum computers. So predicting how a new medicine interacts with human body, which may take so simple example, corona example. During corona, for the corona vaccine, it took 8 months for a classical computer to predict or to find that vaccination. But whereas in quantum computer, it may not take more than hours or days, for optimizing global airline schedules, for simulating behavior of complex molecules, for breaking or strengthening model encryptions, forecasting climate patterns with higher accuracy. These problems may take years for classical computer. That is what I've been mentioning. For example, let us say in the next minute it is going to rain. It should rain. But whereas in classical computer, it gives the prediction, not gives it won't give the accurate thing. If the next minute it is going to rain, it will not rain as per the classical computer. Why? Because the model is trained on the past data and it will be predicting based on the past data. That's it. Okay, that is why classical computers are failing to give those things, but whereas a quantum computer can give us everything. Okay, that is what about why we require uh, quantum. So strategically, why we require quantum is nothing but, so already many countries have started the building the quantum infrastructure in their countries. Why? Because if someone hacks our RBI system, let us assume. So our RBI system or other our phone pay or our WhatsApp or any other social media is nothing but end to end encrypted. So if someone hacks it, so we strategically, for example, if USA wants to hack our system, let us assume. So USA wants to declare a war on India. Just assume. So what does they do? Uh, they don't directly send bombs onto us. They indirectly hack our system. Then strategically they hit our system such that we'll be standing beside them like nothing. Why? Because strategically they hit our system, which means we are nothing. If they hit our system, we are nothing. So strategically, that is the reason we require quantum. Strategically, if we wanted to prove ourselves, then the quantum system should be evolved and developed in India also. That is the reason we require strategically quantum in India. So I've been given here. A technology is strategic when it is important for countries' national security. That is what I've been mentioned. National security, economy, scientific leadership. So now, as of now, the country which is having a quantum computer is more powerful than the country which is having a nuclear bomb. So try to understand the importance of the quantum. Okay, technological independence. Countries investing in quantum today are preparing for future economic and security advantage. That is what I've been mentioning. So if you wanted your system to be encrypted in future, then you need require quantum computers. So in strategical, first thing is nothing but national security. So modern communication depends on encryption. Why? Because even a prime minister needs to communicate through classical internet. The classical internet is not at all safe in right now. It can be hacked. So for that communication, we require quantum technology. So it can provide ultra secure communication, quantum key distribution, and detection of hackers. So if someone wants to measure my information, then the information will be collapsed, which means my information is 100% secure. That is the reason we require nation for the quantum scientific strategically we require quantum. And then the second point, cyber security. So today's internet security relies on mathematical encryption. So powerful quantum computers could eventually, so not put, could eventually break some currently used encryption methods. So therefore countries are also developing post quantum cryptography. So this is what you need to remember: post quantum cryptography. Post quantum cryptography in the sense, cryptography is what we are using right now. Where you end-to-end encryption uses cryptography. If quantum computer has been developed, that end-to-end encryption will be also break. So to avoid that, the scientists already started creating post quantum cryptography, which is the advanced version of cryptography. In the next year, you will be able to know what is cryptography. Or in the future classes, I will be teaching the overview of a cryptography. Also, no issues. And strategically, we require for economical growth, we require quantum. So quantum technology is expected to eventually uh, could create new industries in computing, healthcare, banking, telecommunication, manufacturing. This will generate new companies, high skilled jobs, etc., etc. That is why strategically we require quantum. Now moving on to the scientific significance. So quantum technology help us scientists to understand nature more efficiently. So atoms and molecules. This I am talking about atoms and molecules, which are very tiny particles and which are very sensitive to. So scientists can simulate these complex molecules experimentally. So why we require quantum? Why? Because if we need to have the more qubit system, then if you want more qubit system, scientists should have that infrastructure to develop. So for that, scientifically, we require quantum. So applications for, if that happens, we can discover drugs. We can discover prediction analysis, for example, weather prediction with accurate predictions, and even material science also. So that is why we require scientifically we require quantum. And for solving scientific problems, we require quantum, Nana. That is what I've been mentioned here. For better scientific results, we require quantum. And another one is nothing but strategical, scientific, strategic, and another one is technological, right? Technological is here, right? Technologically, why we require quantum? So technologically, we require quantum is nothing but in for quantum computing. So quantum computing falls under quantum computers, Nana. So quantum computers can solve certain optimization and what is this civilization, civilization, sorry, it is not civilization, and cryptographic problems much faster than classical computers. Applications include artificial intelligence, machine learning, drug discovery, etc., etc. And this technological significance is nothing but this technological significance comes under quantum computers, quantum communication, and quantum sensors. Okay, these are the three things we require quantum computing technologically. So quantum communication is nothing but I need to communicate from India to some other in country. So the communication should be secure. For that, I require quantum communication, and I want to transfer my information through internet. That is why I require quantum communication. Okay, and another one is quantum sensing. Quantum sensors are nothing but the sensors that predict nature or that predict the weather. For example, I placed a quantum sensors in Karnool, and that should predict uh, the next minute weather forecasting. For example, in the next minute it should rain, then it should rain. In the next minute it should be sunny, then it should be sunny. That is how the accurate the quantum sensors will be going to be in the future. Okay, why? Because recently you have seen at day before yesterday I think in the Nepal, due to floods, many people have been dead, right? So for that, if there is a quantum sensor present in that area, then it can predict uh, uh, what do you say, that floods early itself, such that the people who are there living can vacate or can go for the shelters for another area, so that the cost of the cost of deaths will be less. So for that we require quantum sensors, Anna. Now moving on to the next topic, a snapshot of quantum technologies are nothing but again quantum computing, quantum communication, and quantum sensing. Before going on to that, is that clear for everyone till this particular topic? Why I'm moving fast? Why? Because the time is running fast. I've been expected to finish it by 7:30. By now it is 8 o'clock. So Nana, is that clear till this particular topic? If you're having any doubts, let me know in the comment section, Nana. So quantum technologies are nothing but again quantum computing, quantum sensing, and quantum communication. These are the three things again we need to learn. So quantum computer is nothing but that uses qubits instead of bits to process information. So classical computers, quantum computers use superposition, entanglement, quantum interference. So uh, in classical computer, the process will be sequential, one after another. So whereas in quantum computer, the quantum computer will be showcasing the parallelism, which means the parallelism will be allowed using superposition, which means at the same time we are having more states at the same time. That I am calling it as quantum parallelism. So suppose we want to find the shortest path to kernel. This example, please read, Nana. I don't go through this example much. So try to read. So applications include drug discovery, AI, financial modeling, weather prediction, material science, etc., etc. So companies which are working on quantum computing is nothing but IBM, Google, Microsoft, Intel, Rigetti, and IonQ. Please remember these company names, okay? So which are very very important. And moving on to the second type is nothing but quantum communication. So quantum communication uses quantum particle. Usually, in quantum communication, we'll be using photons. Why? Because photons will be traveling with the speed of light. So we can transmit our what do we say, communication very fast using photons. Photons are nothing but the packets of light energy to transmit information securely. The main goal is to provide highly secure communication, Anna. That is the main goal of quantum communication. So quantum communication will be relying on entanglement, fundamental, and quantum measurement. Why? Because after passing the information, we should measure the information, right? So it will be relying on two important fundamentals. So if someone tries to interrupt the communication, the state changes or collapse. Okay, this disturbance alerts will be sending to sender as well as receiver. For example, if I am sending hi, then if someone measures it before it is reaching to the second person, then it will be collapsed and sending that alerts. So if someone is trying to see your message, that is why quantum communication is very 100% 100% hack proof. Now, another important thing is nothing but quantum key distribution. So, quantum key distribution is nothing but it is one of the most important application in quantum communication. So, QKD enables two users to share an encryption. For example, let us say if I am sending hi from my hand, in when it is traveling through the channel, it will be not displaying hi, Nana. It will be displaying some for H. For example, for H, it is allocating 10 number. For for I it is allocating 20 number, which means when someone tries to see, they will be able to see 10 20 in the channel. They cannot decode what is 10 and what is 20. Why? Because when next time I am sending hi, it will be another random number. So that randomness gives that hacker confusion. So that's why quantum communication is 100% hack proof. Okay. That is what I have been mentioned. Applications include online banking, military communication, government communication, etc., etc. You try to read it. So quantum sensors are nothing but again, uh, uh, I already mentioned, to measure physical quantities, which with extremely high precision. If I say in the next minute it is going to rain, it should rain. If I say in the next minute if it is going to have sunny, it should have sunny. That is what the quantum sensors are going to say us. So by using quantum sensors, we can measure time, gravity, magnetic fields, electric fields, temperature, acceleration with exceptional accuracy. That is what I am saying. It is not like just giving the temperature, just giving the temperature as classical. So it will be giving exceptionally with high accuracy. So applications that include is nothing but healthcare for MRI. If for example in some still some MRI scans is not giving that accurately, so by using these particular quantum sensors we may get MRI improvements and brain imaging, disease prediction, etc., etc. So quantum sensors can improve navigation systems, especially where GPS signals are weak. So in some areas, GPS signals are completely weak. In such situations, the quantum sensors are going to help in the future. So they can help in detecting underground water, minerals. For example, if I wanted, if someone say here there is water, by using quantum sensor, there will be water in, and the quantum sensors will say you dig 100 meters, there will be water, or there will be minerals, there will be resources. Okay, so the quantum sensors is going to evolve the future. Okay, so a real life example is nothing but for example, uh, 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 in medical field, let us say quantum computing help us in drug discovery, and quantum communication is helping us in, say, sharing patient data securely, and quantum sensing is help us in advanced medical imaging in healthcare industries. In banking industries, in quantum computer can help in risk analysis and optimization. Quantum communication will help us in secure financial transaction, and quantum sensing will help us in quantum secure hardware and timing systems. So these are the things that I have given. Okay. So now moving on to the another most last but not least, national and global quantum missions, Sana. So uh, you need to see here what is a national quantum mission is a government funded program that supports research, education, infrastructure, industrial development. Okay, in quantum technology. So if in that we are having three types. One is India's national quantum mission, which is named as National Quantum Mission (NQM). Is India's flagship program to develop quantum technology. So the quantum technologies are nothing but quantum computing, quantum sensing, quantum communication, and also quantum materials is also one of the most important quantum technology that India wants to develop. It was approved by the government of India in April 2023. You try to remember this years, this complete things. Okay, this mission is aimed to make India one of the leading countries in the quantum research. That is the main idea. So India has allocated approximately 6,003 crores with the budget during the period of 2023 to 2031. So the mission focus on developing quantum computing, quantum communication, quantum sensing, etc., etc. So it also supports some universities such as IITs, IISc Bangalore, etc., etc. Now moving on to the second leading tech giant in quantum is nothing but United States Quantum Initiative. So the US is one of the most global leaders, in quantum technology. So the US launched they in India the program name is National Quantum Mission, but whereas in US the program name is called National Quantum Initiative, which is launched in the year 2018. So the purpose is to accelerate research, education, and quantum technologies too. So several organizations participate. I have been mentioned here: NIST, NSF, DOE, NASA, Defense, DARPA. So these are nothing but the national agencies which are supporting US to evolve to develop infrastructure for quantum. So many American countries are developing quantum computers. Examples include these are all American countries: IBM, Google, Microsoft, Intel, Rigetti. Rigetti spelling is wrong. I is the last spelling. So IonQ. These are nothing but the companies of America which are developing these quantum computers. So Google developed Sycamore. So this is a processor, microprocessor, which has been developed by Google in the year 2019. So which demonstrated a milestone, not mild, milestone known as quantum supremacy. not supremacy, quantum supremacy. So which is nothing but it took only, it took only 100 seconds, but for a classical computer, uh, it may take 1,000 years to do that thing. So that is the main reason we call it as quantum supremacy. Now moving on to another thing is nothing but European Union quantum flagship. The name they have initiated is kept is nothing but quantum flagship program in the year 2018. So try to read all those things, Nana. I don't want to see. Now again, China's quantum program. This is also you try to see. The important point you need to remember is something which they have developed is China's Mesius satellite in the year 2016 itself, which demonstrates quantum communication, and that is the reason we have said that quantum is 100% hack proof. This is what about Unit One, Nana. So if you're having any doubts, let me know in the comment section, Anna. I've been very fast. Why? Because I'm running out of the time. So is that clear for everyone? Is that clear? So that I will stop the class. Is that clear, Nana? Is still any doubts from the unit one? Is that clear, Nana? Please respond. Thank you, Nana. Thank you for the confirmation. So uh, I will be stopping the class, Nana. Okay. So I will be discussing the important questions when I will be teaching in the second unit. Okay. I'll be running out of the time. Okay. Thank you, Nana. So have a good day. Have the dinner. Thank you for attending the class. So please try to wind up. I'll be stopping the live session. If you're having any doubt, let me know in the comment section, Anna. Bye bye. Have a good day.